Ladies and gentlemen, eyes up. All bets are off now. This is Count It In. How many different 9 symbolic codes can be made from the symbols ampersand, 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 @, @, hashtag, and plus sign? Here we are to come up with the possible total number of arrangements that we could do. However, if we talk about arranging all of this, take note that there are 3 ampersands and there are 4 @. What will happen here is that if we are going to stick with this arrangement, just for this arrangement alone, ampersand, 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 we have 4 @, hashtag, and plus. If I'm going to interchange these 2 @s here, will it be a different permutation than the previous one or the original? Take note, if we talk about permutation, even just one object or 2 objects that were interchanged, that's actually counted as another permutation. But what if we are interchanging here the like symbols or like objects? This time we are going to use a specific formula for permutation or n permutations or n distinct permutation. We have here this formula here which talks about the factorial of our total number of objects, n factorial, over the ratio of each of the factorial notation of the number of the objects. So we have here our n is the number of symbols here, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, we have 9. Okay, and then that's our numerator here. We have 9 factorial. However, our denominator will talk about the number of, let's say, d factorial for ampersands, a factorial for @, h factorial for the hashtag, and p factorial for your plus sign. So let's just use d for ampersand. We have 3 of them. Okay, that would mean your formula here will be divided by 3 factorial. Your @, your letter A, is we have 4 of them, so that's actually here 4 factorial, to be followed with our h or hashtag. We have 1, and we have another for our plus sign. We also have 1. This will be disregarded, but just to complete the formula, we have here times 1 factorial times 1 factorial. This is now the time that it will be for us to simplify the entire expression. Take note that if we have n factorial represented by this, which is just equal to 9 factorial, this is the condensed way of writing the product of integers from 1 to n. In reverse order, we have n times n minus 1, the number before it, times n minus 2, until we reach 1. That would mean our 9 factorial is 9 times, we have 8 times 7 times 6 times 5 times 4. Let me just end here, 4 factorial, even if I could still write the rest, because I would see that our denominator, I have here a 4 factorial given here, times 1 factorial times 1 factorial. Automatically, these two are just equal to 1. Now, we have a 4 factorial here. I could extend it to 4 times 3 times 2 times 1. We also have here a 4 factorial, which is supposedly 4 times 3 times 2 times 1. But I can just automatically cancel those two. Because my goal here is, even if I'll be using calculator soon in solving for this, but I could just easily solve for this just by looking for ways such that our denominator will just be equal to 1. 3 factorial here is just equal to 3 times 2 times 1 when expanded, but this is just equal to 6 here, so I can cancel 6 and 6 here as well. So the total denominator now would be just equal to 1, and it's easier for me to simply just multiply the numerators. So you have here the product of the numbers remaining on our numerator. We have 9 times 8 times 7, we don't have 6 because it's already cancelled, times 5. The result of that is actually equal to 2,520. This would be the number of different symbolic codes that can be what do you call this one, can be generated using the given symbols here, and this automatically count the number of distinct permutations that can be formed when we have to consider the objects that are similar. So this is how we answer situations where we have distinct or like objects under permutation. And that's Count It In! Talking about getting the luck of the draw. For all in, subscribe now!